So good day, everyone. For this week's seminar, the Atoms Group is pleased to have Professor Lourdes Vega. She's the director of the Research and Innovation Center on Carbon Dioxide and Hydrogen, and a professor of chemical engineering at Khalifa University in Abu Dhabi in the United Arab Emirates. Also, she is the editor-in-chief of the Journal of Molecular Liquids. She has developed her career between academia and industry with positions in the USA, Spain, and the United Arab Emirates. She is founder and CEO of the Alaya Tech company for the development of sustainable products. She is an expert in molecular thermodynamics, the author of Soft SAFT, one of the most accurate versions of SAFT. She is author of more than 200 scientific publications and 5 patents. She has raised more than $50 million in research grants related to clean energy and sustainable products. She has received several international awards and recognitions for her work on bringing the fundamental science to the industrial applications, focused on environmental solutions. In February this year, she received the Mohammed bin Rashid Medal for Scientific Distinguishment for her contributions in clean energy and sustainable products. So welcome, Professor Lourdes. Thank you for being here. You now have the word.
Thank you very much. I will share my screen. Can you see it?
Yes.
Okay, very good. So thank you very much for the invitation. I will start by the end. I want to thank Professor Tavares and all the Atoms team for the invitation and for allowing me to spend this time with you. And to all of you for being here, because I'm sure you had also other possibilities and you decided to attend this seminar. I want to thank the co-authors and collaborators in this area, the people who have been mostly involved for the one I'm going to present today are Daniel Bamon and Ismail Al-Khatib. But I have several other people in Abu Dhabi working in this field and some professor collaborators. So students are Honyu, Noor, Yutin, Ahmed, and then Ahmed Al-Hajjaj, Muhammad Abu Zahara, and Mariam Haril. And of course, I want to thank my collaborators from many years and current collaborators, Joao Coutinho and Emmanuel Crespo, both of them here today. I'm very glad to know they are here. And also Felix Jobel, Luke Pereira, Santiago Builes, Concha Domingo, and some others, and the funding that we received. You see the photo of the group from last September, and you can see it's very international. So I think there are 10 people from 10 countries in the photo. So I always start by saying, where are we? So if this is the map, you are there on the left, and I'm here on the right, okay? So it's a long distance, and that's why we have different hours. There is another much bigger difference. Look at the size of Brazil. Look at the tiny country here. So that's, the Emirates is this tiny brown country here. But still it's a very interesting country. So Abu Dhabi is the capital of the country. The country has a population of less than 10 million people. So it's more or less the same population as Portugal, actually. And Abu Dhabi has 3 million. So everyone speaks English here. And we have over 180 nationalities. It's a very nice modern city. I don't recommend to come now. Right now it's really too hot. I think we hit 50 Celsius degrees yesterday. Of course, I don't feel anything because we have air conditioning. Now, a little bit about the Research and Innovation Center on CO2 and hydrogen. We call it the RICH Center, not because we are rich in terms of money yet, but we are rich in terms of knowledge, but essentially is the acronym for the full name. The center started a year ago and is focused on clean energy solutions. We intend to be a world-leading center of excellence in the use of combined modeling and experimental approaches for research and development of novel materials and technologies for CO2 capture and utilization, as well as hydrogen production, storage, and distribution. So the whole research revolves around 4 themes. So we work on novel materials and processes for CO2 capture, part of which I'm going to present today. CO2 utilization, that we can leave it for another day. We have several interesting projects in this area as well, in which we work either on photocatalysis or electrochemical conversion of CO2, but also of direct applications of CO2, like for example, from waste to materials using CO2. We work on hydrogen, materials for hydrogen production, storage, and also on the optimization of the distribution. And the fourth thing, which is also very, very important, we work on outreach, exploitation, and dissemination. So this seminar is actually part of that, no? Explaining a little bit what we do. So in addition to CO2 capture, hydrogen, and utilization, we work in the general area, of advanced materials, nanotechnology, multi-scaling, and clean energy. The center is a large center. It's integrated by 18 faculty from the College of Engineering and the College of Science. And in addition, we have 60 more scientists between postdocs, graduate students, and engineers. And then we have the support of several international organizations and universities. University of Aveiro is one of them, as you can see there. So we have 6 dedicated laboratories in the center. Some of them are fully in operation. Some of them right now, no, because we were in Masdar, but we have moved to another building, and with the COVID, everything stopped. And in addition, we have some core laboratories. But I'm not going to talk more about the center because I want to talk about CO2. So why are we worried about CO2? We have this beautiful planet on the left. The problem is that this is how the CO2 emissions are affecting the climate change and the temperature of the Earth. So we have to do something with this because it has been proven, completely proved now, that part of this is due to the human activities. So I always, every time I give a talk, I use the same slide, and I always update it the night before I give my talk. So here is the slide. 12 years ago, 13 years ago now, I started to check what is the CO2 concentration in the atmosphere as measured in the manual law from the NOAA. Okay, so what you see here is the CO2 concentration versus 5 years. Okay, the red line is the monthly means average value, and the black line is the same but corrected. And by the way, here you have the link that I use every time I give this talk. So on the right hand side, I don't know how to move this because, okay, I don't need to see myself. Okay, so on the right hand side, you see the same plot, but now this plot was taken yesterday, okay? And what you see here is, it looks very similar. Now it's from 16 to 21, but look at the numbers. See, here we are below 385. Here we are above 415. As I say, the numbers are from, I took them last night, and the last update was in June. So even though with the COVID and the confinement, people are talking, you know, the atmosphere is much better, and it is. The reality is that once you get the CO2 into the atmosphere, it lasts for many, 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 many years. And here you have the numbers. So here you have the last data from last year, from this year, sorry, from last year and from the year before. And continuously, we have an increase. The bad news are actually that the first time in recent history that we hit it continuously, more than 410 has been now. And this number is the highest number achieved in the last 3 million years. This is only measured in manual, but the global measurements are also growing and growing. So this data is from March, and you see always the increase is at least 3 ppm. So maybe 3 ppm you don't think is important, but it has a direct connection in the increase of the temperature of the Earth. Where are these? So this is a direct connection with the greenhouse emissions. So the CO2 may look the bad guy of the movie, because if you look at this here, this is the CO2 is the huge amount of gases emitted into the atmosphere that are impacting the climate change. But it's not only that. We also have methane, we have nitrous oxide, and we have the fluorinated gases. That even though the amount of fluorinated gases is very small, the global warming potential of them are huge. If we look at the sectors from where these greenhouse gases are coming, we can see that there are different sectors. Some of them are more diluted, some of them are more concentrated. But if you look at this distribution by impacting the electricity and heat production, the industry and the transportation, we get most of them. If you look at the emissions globally, you can see that the biggest emitter today is China, followed by the United States, the European Union, India, Japan, Russia, and some other countries. But these numbers keep changing, okay? So what do? I always paraphrase one of my favorite scientists of all the times, Albert Einstein. He say, those who have the privilege to know, as we do, have the duty to act. So what can we do? There are different things we can do to avoid the CO2 emissions into the atmosphere. Some of them we can do as scientists, some of them we cannot. We cannot directly, but we can do indirectly. For example, the policy implementation. In the policy implementation, like the Kyoto Protocol, for example, Montreal Protocol, the F-gas regulation, they force to reduce these emissions. Of course, another thing in the hands of all of us is to preserve the CO2 sinks that we currently have. We can work on alternate sources of energy that will be less CO2 footprint. We can work on energy efficiency and energy saving. We can capture the CO2 before it goes into the atmosphere and utilize it or store it, or we can work on sustainable processes and products that will have a lower impact because they will work with low global warming potential components. So today I'm going to talk essentially about carbon capture. There are two technologies that are mature for CO2 capture. The one that is used in industry mostly today is the absorption by aqueous amines. This is the most used technique, which means the cheapest at the large scale. However, it has some limitations that preclude using it for a huge CO2 capture like the one we need, for example, for capturing CO2 from a power plant. The main ones are that because it absorbs very well, it is very difficult to dissolve. So this means it's energy intensive. Energy intensive process means money if the energy is expensive. In addition, the amines degrade in the presence of oxygenated compounds that usually come with the CO2, such as SO2, NO2, etc. And there are some lost amines with evaporation. On the right-hand side, we have the possibility of doing adsorption, which has the potential of reducing the total cost by 30% while overcoming some of the technical limitations of the amines. Then we can use swing absorption cycles like pressure swing absorption or temperature swing absorption, which can represent a very good advantage over what we have. So what are the needs if we want to improve the absorption? I already have said the limitations. We need best processes or change the operating conditions or new solvents or blends that will overcome some of the limitations here. For the adsorbents, we need adsorbents with high capacity, high selectivity. They should be stable, and of course, they should be cheap. There is an additional problem with the adsorbents, which is how do you manage such a huge amount of adsorbents that you need for the columns for the amount of CO2 you need to capture. But this is more on the engineering side than on the scientific side. These both technologies are used today in industry. Solids, not at that large scale, but zeolites are the ones that are used, for example, in industry for the separation of CO2 as an impurity when you do air separation. But the title of my presentation is the application of multiscale modeling to the design of materials for CO2 capture. So how can these molecular modeling tools help on doing that? Well, there are two things in which molecular modeling can always help. And I mean, I'm talking to an audience where all of you are converted because all of you work in this area more or less. So I don't need to convince you, but it's good to go through that. So first, they help in understanding the fundamentals, so the molecular interactions and the structural effects on the thermodynamic and transport properties that will guide the behavior of the processes. They can actually guide in the selection of the best solvent blends or adsorbents for a given application. And on the application side, they can help us to obtain properties to complement the experimental data. They can help us to generate data for process design. Now, I'm going to show you how I explain this to my students, and maybe this is the only thing you will remember at the end of my talk, but this is a good message. So what is this? This is a cat. This is a beautiful cat. What is this? This is also a cat. And what is this? This is also a cat. So the three of them are cats. However, this is the real cat. This is a very detailed model of my cat. And this is a very coarse-grained model of my cat. So not all models have the same degree of accuracy, but they all represent the reality. In this case, these two guys represent my real cat. And this is what I'm going to use through the presentation. So what do we do to model these absorbance or adsorbance? We work in a scale from angstroms to meters. So we use molecular modeling tools to model the amines or the solvents and the CO2 interactions with them, or the solid materials and the interactions of nitrogen, CO2, and impurities with them. And then we work on the process simulation. In most of the cases, we use the data from these models to complement the data we need to do either the design of the absorption column or the absorption columns. The work I present today, as I mentioned, is essentially done by Ismail, who is a PhD student here in Khalifa University, Dani, a research scientist in Khalifa, who was actually my PhD student in Barcelona, and Luis, who was a student of Joao in Aveiro. And then he went to Edinburgh and he came here as a postdoc and he's now working for Total. So the first tool I'm going to explain that I'm sure you are familiar with it, but I don't know how many of you have used it, is actually the SAF equation of state. So this comes from the statistical associating fluid theory. It's an equation of state based on Wertheim's theory, and it allows you to calculate the total free energy of the system as the summation of different contributions. So this is the monomer term, but this is the residual, so you need to add the ideal contribution. And here you have the handful free energy, the monomer contribution, the term that you have by the formation of a chain, if you have chains such as decane, for example, association, if you have decanol, for example, or a polar term, if you also have a dipole. Then these are the terms in which it differentiates this equation from a cubic equation of a state, for example, because here we have the molecular information. So here we have the radial distribution function, in which it tells you how the different groups are connected in the chain. And for the association term, this capital X that we have here tells you how many sites are not bonded, which in the end, by differentiation, you get how many of them are bonded. So it tells you the hydrogen bond information. This equation was developed in 1997, and we use it throughout the day. So in order to apply this equation to experimental systems, and by the way, by differentiation, you get the pressure and the chemical potential, so you can use this as any other equation of state. In order to apply this to experimental systems, you have to define your parameters. So the equation for associating fluids has 5 parameters that may look a lot, but it is a lot, but we don't fit them just fitting. What we do is use the physical information that they provide and try to transfer them as much as possible. So M, for example, is the chain length. So it has to be consistent with the real molecule and modeling. Sigma is the monomer diameter. So it's the spherical size of the groups making my change. Epsilon is the dispersive energy, and epsilon HV and kappa HV are related to the volume of association in the case I have hydrogen bonds. How do we fit them? We define the functions in which we fit them to experimental data, usually paper-liquid equilibrium data, if it is available. If not, we use density pressure data, for example, or in some cases, we also use derivative property data. So we define the functions in which we minimize the differences between the density calculated and that experimentally obtained, and we also equate the chemical potentials in this case. The beauty about the equation, for example, even though if you don't use it as a group contribution method, is that these parameters correlate very nicely with the molecular weight. So if you have some members of a regular chemical family, then you can predict the rest of the series of the family. Also, you can transfer them between families. The additional benefit of using an equation of this type is that you can use it not only for vapor-liquid equilibrium calculations of solubilities, but you can couple the theory to other theories in order to calculate other properties. For example, by using a renormalization group theory, you can very accurately calculate the critical region, as you can see in the plot we have here. This is with the crossovers of SAF. We can also calculate interfacial properties, like the one here, coupling that to the van der Waals theory. Then you can do ion treatment, polar reliability, derivative properties, excess properties, etc. So let's see how we apply this for the CO2 capture. So I'm going to divide my presentation into solvents and adsorbents, and I'm going to give you some examples of both. So in order to model the CO2, for example, this is the model we use from SOFSAF. So we have the groups that I mentioned before, and we explicitly model the quadruple. For the case of water, we have different models. The model we have used here is a four-side model in which we represent the 2 electrons by 2 associating sites and the 2 hydrogens by 2 other associating sites of different types. For the MIA, for the amines, what we do is we put explicit groups mimicking also again, explicit associating sites mimicking again the chemical groups that we have in the molecule. So for example, here we have the NH2 is represented by nitrogen and 2 hydrogens, or the OH group is represented by an oxygen and a hydrogen. As I say, we try to build as much physical information as we can. So for example, in order to model the interactions of the amine and the alcohol groups, what we did is we isolated the groups that we had from previous groups, from previous molecules we had studied, and we built our models for MIA. So the association parameters, for example, for the OH group and for the N2H group were transferred from the amines and from the alcohols. Here you have what we did. So we transfer these parameters, for example, the epsilon and the kappa for the association from the amylethane and from ethanol. And we just fit it to the experimental data, the M, the sigma, and the epsilon, which are the ones related to the van der Waals forces, more or less. So from now on, unless I specify something different, the symbols represent the experimental data, and the lines will represent the staff calculations. So this is how these parameters behave for the temperature density diagram or the pressure temperature diagram. However, pure fluids means nothing. Now we have to move into binary mixtures and ternary mixtures. So for this, we also have to model the association between the different groups. So here is for the ethylamine water, for example, and here is what we have for the ethanol water. For the ethylamine water, the predictions were not very good. You can see that here. So we needed to fit binary parameters for them, which are the the 2 lines, the blue and the red, are 2 approaches we use for fitting the parameters, and that they were transferred for the ternary systems and for the binaries at other conditions. Also, the details of the papers, I always put them here so you can go to the references. This is how the results that we obtained for the ethanol water systems compared to the experimental data. And now we have to put the CO2. So what we did is we modeled the interactions of the amines with the CO2 by a cross association in this coarse grain model. So the CO2 doesn't have association with the CO2. It just works these interactions as always, but when it interacts with the amine, we put these association interactions to mimic this. With this, we got these beautiful results now for the partial pressure versus the CO2 loading compared to the experimental data. The results are very good for the low range CO2 loading, but remember this is too high for the industrial applications, and we didn't fit them. So, I mean, we can have a fitting for each temperature. We fitted one temperature, we predicted the others. We could do it better if we fit all of them, but then what is the purpose? Because then we cannot transfer. We predicted very nicely. I mean, it doesn't go through the points, but it captures very nicely the enthalpy of absorption for these systems. So once we had this for MIA, MIA is the one everyone knows and is the one that it works. So how do you use this for new solvents and new blends? So what we did is we went through the literature, we built a database, and we found out of more than 150, actually this was done 3 years ago when Luis came. Now we are just updating right now with Ismael and Daniel, the database. We have many more systems now, and actually we have observed different better possibilities. From the database we built, by defining some key performance indicators, we pick up five amines that would be very good for CO2 capture. So here you have, for example, the loading versus the enthalpy of absorption, in which we plotted all of them. The line in 1,1 is the MIA, so it should be as good as MIA or better, and that's the ones that we put with the stars here. So these are the ones we have studied and for which we are going to show some results. So how do we do this? Because now we have many groups, many parameters. So again, following this procedure, what we wanted to do was to screen them using as less fitted parameters as possible. So what we did is an approach similar to what I explained for the MIA, for the other amines, and then we modeled them using these functional groups, and then we modeled their interactions with water. So first we had the pure component parameters, then we studied the aqueous mixtures, and then with that we went into the CO2. So we predicted the CO2 in the blend. Okay, so the models that we use are similar to the ones I explained right now. So for each of these molecules, we have to specify the groups that we have in the molecules. Then if we have multifunctional molecules, we have to do the same for them, okay? So with this, we predicted the properties. So here, for example, you have the predicted properties for the amine solutions using soft SAF versus the experimental data. And you can see now the vapor-liquid equilibria, the density, the enthalpy of mixing, the viscosity, the interfacial tension, and also the blends. As I say, the details on the calculations are in the papers I'm showing here. And really, the results look very promising. So how did we model the chemical absorption? Because, you know, CO2 really reacts with these amines, and depending on the type of amines that you can have a carbamate or a bicarbonate. But SAF doesn't have chemical reaction because it's a physical model. So what we did actually, we used implicit reaction schemes with physical aggregation. And that's the beauty of SAF. When you use this association, means these highly directional, short range, strong interactions that can mimic this type of interactions as we have for the carbamate and the carbamate formation. So this is actually what we did. And this is why we put these two associating sites into the CO2 that I mentioned before, to mimic this physical aggregation that we have. Does it work or not? Well, that's what we have to see. No? So with this, we had to calculate these parameters for these models. And we did following an approach similar to what I explained for the pure fluids, but now using the mixtures. So we fitted the parameters, we fixed this value for the association for all of them, and we put this epsilon of aggregation with two possibilities, either a fixed value for each amine, or we put them depending on the temperature. And the reality is that really the dependency on the temperature is not that big, and the results are very, very nice. So we fitted them and we got these very nice results now for the different amines. So this is for PP design, for example, this is for MIA, these are different concentrations, and these are pure predictions, what you see here, okay? What you see here on the right, on the left are what we use to fit. Oh, okay, many molecular. So how do we go to the process conditions modeling? So for this, we define the cyclic working capacity, which is the amount of CO2 that is effectively separated in the mixture, which essentially is the difference between the absorbed amount of the feed gas, partial pressure, and temperature conditions, minus the absorbed amount at the operating regeneration conditions. And we also define the energy index, which is the required energy per kilogram of CO2 dissolved in the rich conditions to the lean conditions. Essentially, the energy of regeneration that is needed, which is related to the sensible heat, the evaporation heat, and the absorption heat. And of course, with the cyclic capacity that we calculated before. For this, we have used a shortcut method by Kim et al. The details again are in their paper and in our paper. And all the calculations for this data were done using SAF. Okay, so here you have now the cyclic capacity, and you have here the energy of regeneration on the right-hand side for the CO2 at different conditions, 5 kilopascals, 10, or 20. And you can see very nice, so our MIA is the benchmark amine, and the rest, we have done all of them with 30% aqueous amine, except for these two blends that we have here. What we can see actually is that the energy savings of these blends, for example, is up to 26% compared to MIA, and the separating is up to 42% compared to the CO2. This data we can compare at the same conditions because we can generate all this information from SAF, even if there is no experimental data for that. Then we extended this to water-free solvents using a very similar approach. So here we have studies on physical solvents like ethylene glycol, methyl ether, ethylene glycol that Emmanuel knows very well, all these compounds as well. We use a similar approach with the soft soft that I mentioned before. We predicted the binary mixtures varying the amine composition, as you can see here. Again, the symbols is experimental data, the lines are the soft soft calculations. And we were able to calculate also the solubility of the CO2 on these amines with glycols at different concentrations with a very similar approach, okay, as the one I showed you before. What I want to show you now is the comparison of all of them. So now we have the solvent cyclic capacity and the energy index for these alternative aqueous amines at different conditions. We have assumed for these calculations the volumetric units with cubic meters of solution, all of them containing 30% amines and 70% of the co-solvent, in which we can assume the same volume of the adsorbent, and then the supercolumn operating is at 200 kilopascals. So here you have the energy versus the cyclic capacity, in which we have the dark highlighted spheres are all calculated for the different solvents that I mentioned, the amines, aqueous amines, and the physical solvents at the temperature of 300 K, all of them, the regeneration temperature. The dashed spheres means the maximum cyclic capacity achieved at this T-lane, and the colors in the background represent the regeneration at lower regeneration temperatures. This is the one we are calculating, these are the other ones. Where do we want to be? We want to be in the square that I put here. And by the way, this is a 25% CO2 concentration. So what we want is to have high cycling capacity and low energy index. So we can see that there are some physical solvents actually that give us these conditions that we want. And we also see that the AMP with water is also in this part. So now I'm showing you exactly the same, but now with 15% CO2. And what you see is that the amines, the solutions now, the solvents are changing. So they're still in the same square, but the values are a bit different. And the same happens when I have 5%. Actually, for 5% CO2, which is what we will have, for example, for a natural gas plant, the energy that we require may be good, but the cyclic capacity is low. Too much for solvents, so let me give you a few words on adsorbents as well. So for adsorbents, what we have been using is molecular simulations. Here is a very nice paper by Christopher's group that was published 11 years ago, in which you see the capacity of the materials versus the temperature and how they are. So you can see that organic hybrid materials, for example, require low temperature or this range of temperatures, some of them with high capacity, some of them with low capacity. And then you have calcium oxide, for example, and lithium zirconate at very high temperatures. However, for low pressure CO2 capture, the conditions that you need are these ones. The materials that are used are MOF, zeolites, and activated carbons. So we started this project several years ago, in which when Danny started as part of his PhD thesis, actually, in which we explore all possible MOFs, zeolites, and some activated carbons for CO2 captures at the same conditions. So in this case, what we have is a little bit more refined cut, okay? Because we were using predictions, so we don't fit things here. We got a force field for the molecules, a force field available for the molecules, a force field available for the materials with the crystallographic information. We calculated the absorption isotherms. We compare with the experimental data. It gives very nice results. And then with the best accurate force fields, we just use molecular simulations to do all the calculations. So here you have, for example, the CO2 capture for all these materials. Let me explain what we are looking for. What we are looking for are materials that will have a sharp increase here, which means that they are very attractive because they will absorb them at low pressures. But we also want them with high capacity, means that they want to get a lot of CO2 inside, which is this part of here. So here you see two very nice materials, the zeolite, which is the one that I told you is already used in industry for CO2 separation. And you also see a very nice MOF, which is becoming very famous in all studies, which is magnesium MOF 74. You can also calculate the heat of absorption, and you can also see we, of course, need high isosteric heat of absorption, and these two materials are also very good. So once you do this, you can use the calculations from molecular simulations combined with some process design ideas to calculate the breakthrough curves. Again, what do you want? You want to have the best desorption, I mean the most CO2 desorbed from your material. So very nicely here, again, the two best ones are magnesium of 74, the zeolite, and then there is a ranking of some other materials. So what we did here is we plotted the CO2 capacity versus the dimensionless breakthrough, and then we get that the best materials are these two materials, which we knew. However, these two materials have a very big problem. They are hydrophilic. So if you get a little bit of water, forget about getting CO2 inside. The whole material is full with water. So you either put another adsorbent for removing water, or you look for other materials. In any case, since that study until today, the MOF has progressed immensely. So we have done this very recent result. These are from 2 weeks ago, in which we have explored the MOFs now and some other zeolites, activated carbons, and materials. And you can see that still MOFs, MG74 gives very nice results, but all the MOF gives very nice results in terms of high capacity and high absorption as low pressures, as I mentioned before. Zeolites are also very nice. So what we did is we compared not the pure CO2, but the CO2 at the same concentrations as I showed you before for the amines. So we did the pure CO2, but also 15% CO2 and 5% CO2. And you can see, of course, that the capacity decreases because you also have nitrogen right now, okay? And you can see, which is one of the beauties of simulations, why magnesium 74 is a very nice material, because it has all these metals available that the CO2 go into there, and the pores are very nicely distributed, okay? So it's a 1D pore in which you can really get all these molecules inside them. So what we did now is to compare the two of them using design tools, using the idea from either SAF or molecular simulations, and doing the process calculations I showed you before for the amines, which are the ones here. So now I'm comparing the CO2 capture using a 15% CO2 in your flue gas, the energy versus the cyclic capacity for both systems. And again, we are looking for this square. So for these materials, for this CO2 concentration, the zeolites are still the best materials, and we have already seen the solvents. So there are more possibilities with the solvents than with the materials. But why don't we combine both of them? So why don't you actually put some amines into the sorbents and see if you can get the best of both of them? So we started to do this again several years ago in Barcelona with another PhD student, Santiago Builes, who is now a professor in Colombia, and he still collaborates with us. The difficulty of doing this in simulations, molecular simulations, not DFT calculations, molecular simulations, because we get this to compare to the experimental data, is how do you model the carbamate formation in this case. So we invented, again, a procedure similar of what we did with SAFT, in which we actually put the two molecules in there. We model this reaction as having already in my system my carbamates and my protonated amines. As you can see here, that symbols, the red symbols are, the open symbols are the simulations, the black are the experiments, and they really overlap with each other. So the simulations give very, very nice results at low pressures and high pressures. So now, how do we do this with MOFs? This is the work we are doing right now. So what we are doing is we are functionalizing these MOFs with different amines, and we are doing this with different MOFs. Again, we are comparing with our wonderful cat the simulations that we are doing with experimental data. This data is very new. I mean, the experimental data is also very new, because this is something that people are starting to do right now. You have to remember what I put here on the right. It may be good, very nice, but actually your amines are using most of your available volume. So it is a compromise between how much amines do you put into your material and how much volume do you effectively leave for your molecules to be absorbed, okay? So here, for example, you can see that, no? That the uptake decreases when you put more amines. So you need to find the right amount amines that you have to put. And of course, you need to look for large pores, because if you have very small pores, it will be full with the amines. So we are working now with these larger pores. As I say, this work is very, very modern. I mean, very few people, if not zero, have done this with simulations. Most of the people are doing experiments, and this we are trying to reproduce this cooperative insertion CO2 in a paper that was recently published in Nature, and that's what we can do with the simulations. So this is what Dan is doing right now. What we realized is that actually the CO2 gets inside into the amines, and instead of forming a carbamate, what it forms is a carbamic acid. So we are modeling the carbamic acid, similar to what we did with the carbamate, and we are getting very nice results compared to the experiments, which is what you are seeing here. The sharp increase, which is difficult to explain experimentally, we could quantify in simulations because we saw there is a critical uptake of 1/18 CO2 molecules per metal site on the crystal, from which you start to see this high sharp in here. And you can also see that experimentally there is no complete functionalization, but we understand there is no need for that actually, because then you will occupy all the volume available. So to summarize, I guess we all know that we have to work on sustainable development, which means to secure this clean energy, but in a nice way. We need to work on this because science and technology are needed. We still need to understand better what we have to do. This is a combination between chemistry, physical chemistry, material science, and engineering. Modeling can certainly be used for this, and understanding the thermophysical properties and the needs is a first step to really model them. So I show you today some examples on soft sap and molecular simulations, but I'm talking to a group that works on applied thermodynamics and molecular simulations. So in the past, we have learned how to develop these tools and how to produce them. In the present, we are using them, but I think the future is also ours, because we still need to think how to use them to work in this wonderful area of sustainable development. With this, I thank you for your attention, and I take any questions you may have. Thank you.
Thank you, Lourdes, for this very nice talk.
Thank you.
Yuri, you're the boss.
So, thank you for the very nice talk. We now open the floor to question. Anyone can enable the microphone and ask, or write down in the chat so we can read it.
Hello, Yuri. May I ask the first question?
Yes, go on.
Very nice talk, Professor Vega. I am curious about what will be the end product. I mean, the fate of these CO2 molecules after you are absorbing them with all these materials. Is there a plan already to use?
Oh yes, there are many plans
to do some transformations.
Yes, I told you we work. So today I wanted to talk about CO2 capture. Then there is a whole area which is CO2 utilization. And in this, we are working on different things. So we are working on using catalysts, photocatalytic materials to convert the CO2 into chemicals, added value products. We are also using electrochemistry or thermal processes as well to produce the CO2, to convert the CO2 into other products. However, you know, this is energy intensive. So you need to, you know, the CO2 molecule is a very stable molecule, which is, that's why we have the problems we have with the climate change, because it lasts forever. So you need to find smart ways of breaking the CO2 molecule or combine it with other things. And in addition, actually using basic chemistry, you can react the CO2 with some other materials to produce new materials. For example, one large project we are working on right now is on reacting the CO2 with the slag from the steel factories to convert that into construction materials. Construction materials are very cheap, but the materials we are constructing right now are aerated materials. So they are very light materials which have very good isolating properties. So It's very good for this part of the world, for example, because it doesn't allow the heat to go in. You can also use CO2. I mean, you are touching my fiber, because that's my favorite topic. So I can talk about this for hours and hours. I even wrote a book that I can give you about this. You can use CO2 for food applications, for water applications, but the large area that I see is combined with for materials production, okay? Even though I have to give you the real numbers. So the amount of CO2 that is, you need to know, the amount of CO2 that is emitted into the atmosphere per year is 30 gigatons, okay? The amount of CO2 that is used today in any application you can think of is 130 megatons, okay? So there is orders of magnitude of difference. There is no way we can absorb. Imagine that we can capture all the CO2, which we cannot, because many of these sources are very, very diluted. That's why we are working on concentrated sources. Imagine 15% is expensive to capture, and 50% is the concentrated sources we are working on. Okay, so there are diluted sources like less than 1%, or the air. No, people are talking about capturing CO2 from air. Okay, the air has, we say, 415 ppms. How do you remove this? This is an impurity. Okay, so getting pure CO2 from air is very, very, very expensive. So first is we need to focus on capturing CO2 from concentrated sources, but we need to focus on emitting less CO2, which is what I say in one of my slides. So we need to move to other sources of energy. We need to move to energy intensive processes. But the area of CO2 utilization is a beautiful area, especially combined with chemicals, okay, and materials. These are the two main areas.
Thank you so much for the very nice explanation. I just have one more question. If you don't mind. I am also curious about one other thing that you told me in the beginning of your presentation, that you have other gases that are also promoting climate change. And if you have these other gases, and for instance, the one with the fluorine that you said that it's in small concentration, but it actually has a very big effect. My concern is how can we establish a cause and consequence problem to the CO2 if we have all these other gases that are also playing a role in the climate change?
Excellent question, Bruno. Actually, when we talk about CO2, we talk about CO2 equivalent emissions. We are not talking only about CO2, okay? I have a huge project on refrigerants, which are these fluorinated compounds. Huge project, which means it's my other fiber. I mean, I really like this topic, and we are working on, again, SAF and molecular simulations for that. So there are, remember I talked about the policies? So the policies for the fluorinated gases are there. By the way, when any environmental agency or government talk about climate change and how to avoid that, they don't talk about CO2. They put all these greenhouse gases that I mentioned before, okay? So methane is there and the fluorinated gases are there. The Montreal Protocol is the one, okay, so I give me 30 seconds to explain this of the refrigerants, because I think it gives you a dimension. So the refrigerants started a little bit more than 100 years ago, okay? The first refrigerants, actually CO2 is one of the refrigerants, ammonia is another one. They were propane. They are very inefficient as refrigerants, and they have some safety and toxicity issues. So in the early 1930s or so, they invented the chlorofluorocarbons, CFCs. They solve all the problems the refrigerant had, okay? So very efficient, no toxicity, no flammability, excellent. But then it was demonstrated again by science, and they got the Nobel Prize, that they are the ones causing the ozone hole in the ozone layer, okay? And it's demonstrated, these are chemical reactions that provoke that. So then the Montreal Protocol forbid them. So they remove them from refrigerants, so they have to invent other refrigerants, and that's where the hydrofluorocarbons came. No ozone depletion. But now, in Kigali, 4 years ago now, it was decided that we have also to phase out the hydrofluorocarbons, which are the ones we use right now in our refrigeration applications, because they have a very high global warming potential. These are fluorinated compounds. They have thousands compared to CO2. Okay, so we are now working on finding new refrigerants with a much low global warming potential. Again, you need to know a lot of chemistry, but you also need to have different skills. We are working with this on finding blends, because there is no pure compounds. If you go into the periodic chart, the possibilities are very limited. So you need to have blends that are isotropic blends. So thermodynamic is key to develop this, okay? So yes, there is a whole, in Europe, we have actually the F regulation, and that's why now all cars have refrigerants that are very new refrigerants, and there are two companies that are becoming rich because they are the only ones with the patents for that, which are the hydrofluorocarbons, the hydrofluoroolefins, okay? So don't worry, they're taking care of that, but we all have to take care of that.
Thank you so much.
More questions?
So, Raimundo, he's attending from YouTube, and he's asking, what's the maximum temperature for using the MOFs?
The maximum temperature for what? For the CO2 capture? Okay, so okay,
the MOFs metal organic frameworks.
This is a very good question. It's not the maximum temperature. So you have to check the capture, the absorption and desorption at the conditions of the process. Okay, so it depends on the process. Usually what we do is, I think I show it to you. So you absorb at ambient or 303, for example, Kelvin, and we dissolve, the maximum we dissolve was 400, but this is given by the process at which you are doing that, okay? And it's directly related to the two indexes that I gave you, the cyclic capacity and the heat of regeneration. In principle, if what you are asking is about the mechanical stability of the MOF, that's a different issue. It's not related to the temperature, it's related to the process itself. Some of the MOFs breathe and some of them are very fragile. So when you do the absorption, desorption cycles, they may break, okay? So actually another area in which we are working right now is combining MOFs with other materials, for example, graphene oxide, to improve the mechanical properties of the MOFs, but not because of the temperature, but because of the mechanical properties.
Okay, thank you. He won't be able to reply because he's on YouTube. So any further questions?
Can I ask?
Yeah, of course.
Yes, of course.
Thank you very much, Professor Vega, for your presentation. At first, I would like to mention that we have more than 100 people watching us, both on YouTube and at Zoom. But here's my question. It's just out of curiosity. I don't know if you already mentioned that. If you did, I probably missed it. I'm sorry about that. But when you perform simulations to study adsorption, do you also do dynamics on the solid structures? I mean, for instance, do you allow the MOFs to move and change their structures? Because maybe changes on their solid surfaces or even a solid phase transition may affect the absorption of CO2. So I was wondering if you...
Very good question. There are many MOFs. Some of them breathe, some of them don't breathe. But it also, breathe means that they change the structure or they are rigid, okay? In the calculations we have done, we have used rigid MOFs. And this is because when we compare to the experimental data, we get very good results, which means we are capturing the behavior of the MOF at these conditions, okay? At the temperature and pressure at which we work. But yes, and by the way, maybe not for CO2, but for some other applications, the MOF will really expand and contract. And you can use this as one of the benefits of the MOFs. But also, again, you have to take into account the mechanical stability of this material. So it's a beautiful area because you can understand fundamental science, but then if you want to apply this at large scale or industrial scale, you have to take these other things into account.
Sure. Thank you. Thank you very much.
Thanks. So I didn't mention it. You didn't miss it. You were very attentive the whole talk.
Well, anyone else?
Okay. So Danny, no, listen. Danielle is writing to me that some of the MOFs will degrade after 300 Celsius, but that's too high temperature for us, as I say, okay? Thanks, Daniel. So answering the question on the temperature, for the range of temperatures we use, which are the ones for the processes of CO2 capture, we don't have any issue. But of course, if you want to use them all for other applications, they will degrade at 300 Celsius. Some of them. Thanks, Danny.
Well, there is a question from Professor Richard Elliott in the chat. Would you like to read?
Richard.
Richard?
Hi, yes, sure. Good. Thanks for the nice presentation. Yeah, so I remember a little bit about adsorbents and industrial perspectives on that, and you mentioned that, if I didn't hear wrong, that the MG-MOF 74 is a 1D adsorbent. And what I remember was those tend to be disfavored because once you block that 1D, that's it for that particular channel. And then that just accumulates, and so the lifetime becomes an issue.
This is true. And by the way, I wanted to answer to Tiago, and I forgot. When you talk about dynamics, I thought you were talking also about the diffusion of the molecules inside the MOFs. Okay, excellent point, Richard. So what we have done so far, the calculations you have seen are grand canonical Monte Carlo. So we don't have any diffusion or any issue effect with that. However, as Richard said, if instead of doing just a grand canonical, you are doing real diffusion, and it happens. I mean, if the molecules move as they move experimentally, if the pore is blocked, then they are not going to move. For these, the size of the MG-MOF 74 compared to the size of the CO2 will allow the CO2 to move unless you have another blockage effect, okay? I didn't talk about the impurities. We published a paper last 2 years ago, 2018, in which we studied the effect of the impurities on this absorption, and you can see that some of them are huge. I talked about water already, but in addition to water, you have the effect of SO2, for example, or NO2, that will decrease the absorption because these materials will also be very attractive for these other compounds. Right now, we are the MOF 74 actually is small, but the other good thing about it is that actually it is mechanically stable, okay? Which is one of the points that I mentioned was a problem. So we're still looking for materials, as I say. I show you already materials similar to MG-MOF 74, but with a larger pore in which you can have more CO2 in there, and in which you can also functionalize with amines. So this is actually, this is what I wanted to tell you. This is a very, very active area of research in which we can still do many things. I mean, there is room for many other people to work in this field.
So could I follow up then? So were all the alternative MOFs, they were 1D also?
No. They are all different type of MOFs. No, I think I show you one of them. Some of them are even very similar to the zeolite. So QBTC, for example, is very different. MOF 5, MOF 177, they have very different structures. That's why we pick all of them, because we pick them with the different geometrical properties in addition to the chemical properties.
Was one of them particularly mechanically stable and multidimensional?
No.
So you can have one but not the other.
Yeah, but with the MOFs, you have the possibility of tuning them. I mean, you can have the possibility of having longer linkers, and then you will have more volume available.
Okay, thank you.
Thanks. And we are, by the way, I didn't say, so I presented today only GCMC results essentially, but we are also doing molecular dynamic simulations to study the diffusion.
Okay, there's one more question from Luciene. Would you like to read it, Luciene? Okay.
Thank you, Professor Lourdes. I would like to know about what kind of force field did you use for MOFs and zeolites? Did you use different ones for different MOFs, or did you use a general force field?
For the materials, what we use is the crystallographic information from the database. We we usually tend to use the force fields that are available in the literature. Okay, so and most of these MOFs have force fields that are really available. So it depends. We will use a universal force field if they are not available, or a Drayton, or whatever other people has published before. And usually we need to do the calculations of the charges.
Okay, then you parameterize in the charts, use like a UFF MOF force field for some of them, and then tuning a little bit the charts for getting a very good correlation with the data.
No, for the data is, well, yes and no. It's not that we fit them for the absorbance that we have. We try to get a neutral structure that represents the MOF, okay? Yes. And then we do the calculations with the different absorbance, but it's not that we refit every time we have a different molecule. We don't do that.
No, I'm saying that sometimes the charge on oxygens are different in
Then
it's not a general force field for.
Correct.
Okay. And for zeolites, what force field did you use? The Sofia Calejo or another one?
Yes, Calejo's force field. Yeah, essentially. Also for some of the MOFs, they have also developed many force fields for MOFs as well.
Okay, thank you very much.
Thank you. So this is one thing I want to say. We try not to reinvent the wheel. We try to use what is readily available and try to predict and see if they work. I'm saying that because right now we are fighting with CO, carbon monoxide. Everything we try in the literature doesn't work. So we may need to have a force field. But in principle, we just get the ingredients and we cook. And we do this on purpose.
Yes, but I'm a work a little bit on it, and for me there is a difficult that the variety on the experimental data are huge, and then force field can fit one, get a good result in some data and another for others. Also for zeolite 30x, you have in the low pressure data from very nice groups like Alirio, Brandani, Caleja. They don't match because the structure, it's not exactly the same. The methods for taking the experimental data, volumetric or anyone, and at high pressure, normally they don't have information to convert excess to absolute values.
I agree. So another thing is we first do, before we do any modeling, we actually check all the available experimental data and we compare them. But we do this for both, for the solvents and the adsorbents, because there are many discrepancies on the experimental data. So first we really have to trust we have to trust the data. It means the data, if we have some deviations from some data, we don't consider between the experimental data. We won't consider that data even for our comparison, okay?
Okay. Thank you, Professor.
You can check it in our papers. I mean, if you look at the paper we published in Chemical Engineering Journal 2016, you can see this comparison, okay?
Yes, I take note here from some reference, including that one that you make a checking that are going to publish now between MOFs, and that is very nice paper, and I'm going to look at it. Thank you very much.
Any of you, thanks. If you need anything, send me an email, or you can check, but if you need anything specific, send me an email.
Thank you. Thank you, Professor.
You're welcome.
Okay, I think there's no further questions. Our time is running over, so let's wrap it up.
Well, thanks to all of you. It was a pleasure, really, to be with you, and thanks for the questions.
Thank you for you.
I want to thank everyone for this discussion. Thank you again, Professor Lourdes Vega. for the presentation. So
Wow.
thank you. Bye-bye.